a superposition. There are interference patterns and spins, either nuclear or electronic, in all problems that we were doing here a very little bit and a lot in the other class, were assuming that your spins, your objects are isolated. It's like an isolated one or two spins in the vacuum, where nothing is around. When we like 2 meetings ago, when we started black body radiation, we made an attempt to run away from this paradigm. I don't know if I delivered it sufficiently poor or you remember something, but the concept of the black body, that the box that we considered filled with photons, does exist in thermal equilibrium. So it receives and gives away the same amount of photons, the same energy. So it is not isolated. It gives and takes, right? And this is dramatic difference between quantum mechanics and statistical mechanics, right? So for realistic systems, when you put your glass container, whatever chemical name is on the hot plate, right, it comes into equilibrium, right? It absorbs temperature, it gives temperature back, and it stabilizes at some value. So can we heat the spin? What do you think about it? What happens if you heat the spin? Trisha is doing that. Spin is getting excited to be heated.
Yeah.
Okay. To which state?
To the excited state.
So there is one. If we have magnetic fields, just that it can be very small, just to define the direction of spin along and against, right? There will be two possible states: spin up and spin down. And what happens, like, if we heat up the spin by some mechanism? Patricia tells it goes from ground to excited. Are you still insisting on this, or you may have second thought?
I may have second thoughts.
And what are they?
I don't know. You said something about the spin up, maybe going down. Maybe the spin direction change when you heat it.
Okay. Yeah. Thank you for agreeing to be flexible, but you're still. It sounds like you're still insisting that it goes just from ground to excited. Any more thoughts? And answer on this question will complete this lecture. And since we don't have any more lectures, it will complete my part of the course. But I'll entertain you with some more equations, but they will be just a follow-up of the answer that Patricia was a pioneer to try to answer to. So let's hit the spin. What happens?
So if we're going off the basis of thermal equilibrium,
Yes.
I'm assuming that, and this is just one single isolated spin. I'm assuming it's going to either equilibrate between spin up and spin down, like switching back and forth, or somehow align some way.
Okay. Equilibrate between up and down. Okay. Anyone wants to object or complement this? Benjamin, excellent. Do you feel comfortable or discomfortable with this equilibration between up and down?
So I more have a question. Is it possible for the spin to somehow, once heated, go like sideways or go like in between the two? So equilibrating between the two?
Yes. And in the other class, we will come back to this spin and talk a little bit more about exactly what you're telling, going sideways or in the middle. Yes. Any complaints?
Well, I want to know what's meant by heating spin.
Okay. Can you tell all of us what is flipping the spin?
Flipping the spin is, well,
Natural.
just going from spin up to spin down.
Okay, so if when we had the black body radiation, it means that we had some collection of oscillators, and when quantum is coming in, we go from lower state to higher state. When it goes emits, it goes from higher to lower, right? Same for spin. There are quanta, since energy of spin splitting is typically in the microwave range, it means that it is microwave radiation, flips it up and down randomly. So you're correct that it flips, but equilibrium means it randomly flips it many times and we do not know when and why. So just average flipping. Are you better about flipping this, hitting the spin? Okay. What do you think? How do you like it?
It's fine.
Okay, thank you. Max, do you see any problems with hitting the spin?
No.
Okay, thank you. You were first, but he is closer.
So if it's equilibrating between spin up and spin down, what is the average of that? No spin?
We cannot say no spin, but in average, magnetization will be zero. And average energy will be halfway between energy of spin up and energy of spin down. Okay? And this, you disclosed all my secrets. You have no discoveries at the end of the meeting because I was going to like derive with some advanced equations coming just to this conclusion.
I was just curious, like, As gave a presentation on, I was just wondering, during the presentation you gave, I noticed that spins were moving between states. Does it have something to do with it?
Not really.
Okay.
Are we considering this box full of multiple particles or just one?
Box. So here we are considering black body, which has a lot of photons of different frequency. But it's in some sense it is on a hot plate, right? So it interacts with environment. Now let's consider only one spin 1/2 on the same hot plate. So it is not coherent flipping of the spin with a pulse. It is unknown, uncertain amount of photons of the resonant transitions that come in and out. Does that answer your question? Okay. So I can try to run ahead of a train and draw a picture, but to address the question of story, but it is very, very premature. Then I will work hard in another class for about a month to draw this picture, or maybe a couple of weeks. So did you draw Bloch sphere in your other class, a part of that class? You did, right? Sorry, yes. Bloch sphere, S X S Y S Z, right? So Adam. Okay, so the quantum state of a coherent single spin is point on a surface of this globus of the sphere, and if you were excellent in your homeworks, it is something like 1/3 or 3/4 of the h bar square. I'm just do not want to lie and do like certain distance for the radius of this sphere. So when we speak about quantum mechanics approach, this vector always ends at the surface. But if we, so it can go sideways, as Tori did ask. But sideways means it's even if projection on Z is 0, it's the length of vector is constant. Right? But if we implement statistical approach, the length of vector can decrease and can come to the 0 length. So if you have equal probability for spin up and spin down to be implemented, and we do not have X and Y projections, then it will be 0. It's like traveling to the core of the Earth. Right? And it is a visual figure, but we will need to work on it much more than we can do today. Okay. So what did we learn 2 meetings ago when we started black body radiation? You may remember, or you may just forget it because of your tough schedules, but we did learn a very simple but important tool that serves as a instrument, as a carrier to go from quantum to statistical. And the keyword was partition function, statistical sum. What are other words for it? Partition function, statistical sum. Maybe there are some other names for this concept. And I'm going to just repeat, but it is a good, if I deliver it right, it would be a good take-home message for your class to remember after. It is a replacement of Schrödinger equation and equation to find expectation value in quantum mechanics. So, like, if in regular quantum mechanics, expectation value of operator A is integral psi star operator psi, and then whatever variable in continuous space or in discrete representation, it is summation of C I star A ij C j, right? So continuous, discrete. And connection between these two is that wave function can be represented as eigenfunctions with expansion coefficients. So those are continuous, and this is discrete. So it doesn't surprise you, right? It's a standard thing. But one can continue this line and say that if we have value appropriate of operator appropriate for state I, if you combine this C star and C into absolute value, and on this way it is important than I equals J. And if we rename C sub I as probability that system is in a quantum state I, then expectation value will be the value of eigenvalue corresponding to eigenstate times probability that the system is in a certain state, right? So now we do transition. We tell that instead of isolated wave functions, the P sub I is just Boltzmann constant energy of state I minus ET. And as soon as we do this transition, we are not in quantum world, but we are in statistical world. So as soon as we replace coherent expansion coefficients squared by the Boltzmann distribution, we philosophically come to the situation when system is placed on a stove. So Boltzmann distribution appears from the fact that quanta come in and out. It equilibrates, and there are more dust on the lower shelf, less dust on the top shelf. Okay. Then I'm just repeating what we already did, but it is so important that I do not mind repeating. Then the favorite word of Patricia starts with letter N. Normalization, yes. So if you find expectation value of observable A, we do summation over probability in state I eigenvalue of I, and then to have it normalized, we do summation of I in the denominator. So for normalization. So this normalization factor looks very similar. It is summation of energies over Boltzmann factor. So it is just energy minus first state KT plus energy second state KT and plus so forth if you have more states. And some people call it W, some people call it Z. And the name is partition function or statistical sum. So we do not need to justify importance of this function because without it, we cannot find observables, right? But there are additional background, additional benefits of using this function. When we did with black body radiation, we found that nominator sometimes can be found as a derivative of statistical function. Well, in that case, it was for very specific observable for energy, right? But the energy can be extracted from statistical sum, from partition function, just by taking derivative over new variable, which is 1 over KT, right? So if one introduces this I don't know how to call it. Everyone calls it beta. It's inverse temperature, and it is used as a continuous variable over which people take derivative. So partition function E minus beta E1, E minus beta E2, plus so forth. And if we need to find the expectation value of energy, we can practice a derivative over beta, minus derivative over beta, of the statistical sum. So Boltzmann distribution means that lower lane energy levels will be occupied more, higher lane will be occupied less. And the statistical mechanics, in a very narrow sense, is just applying this equation or similar equations to different models. Right? The necessity of quantum mechanics as a introductory step towards statistical mechanics is that we admit a concept that there are discrete levels, and we get energies of levels for certain system as solution of a quantum problem, right? Rotational, vibrational, electronic, any degrees of freedom. Okay. So we are, I can open brackets, but it is self-evident. So by taking the derivative, we will get, so taking derivative over beta of the first term, we will get the everything except beta as a factor. So E1, right? And then we will reproduce the exponential itself, minus beta E1 plus E2, E minus beta E2, divided by E minus beta 1 plus exponential minus beta E2. So if there are more than two states, we'll have continuation of this sum, but the reason to study heated spin is very selfish from the point of view of instructor or any investigator. So 2 meetings ago, we, I don't know, enjoyed or suffered summation of geometric progressions, right? Sometimes progressions do not converge. Sometimes they do, sometimes they don't. If we speak about spin, there are only 2 quantum states, and all approaches of statistical mechanics can be applied immediately with the power of anyone who took calculus, right? So one can do several considerations. So we already have a new powerful tool, hopefully powerful. And now we may want to design a scientific question. Which research question, hopefully related to real life, we may want to address with this new tool. So the population of individual states of spin is already addressed in this statement. So if you just plug in any temperature, we need to first, before we go forward, we need to define what is E1 and E2, right? And we can tell that I don't know, Hamiltonian is minus magnetic moment times magnetic field, right? And then as we have magnetic field, the energies will be just offset by the value of this Zeeman splitting. And now this spin placed in magnetic field can be also affected by a hot plate or something that we colloquially can call hot plate. So at 0 Kelvin, if you just plug in this Boltzmann constants and divide by their summation, you will get that populations are going to be at 0 Kelvin, lowest state is full occupied and top state is not occupied. So individual occupations is not unobservable. We want to formulate, excuse me, something more ambitious. And our ambition is to find expectation. Let's just set up what we can find. Expectation value of energy as function of temperature. Maybe a derivative of expectation value of energy as function of temperature. And before we go further, let me interview Adam. What is a derivative of average energy over temperature?
The derivative of average energy over temperature.
Maybe not literally, but which associations, what do you remember from other courses that you took, or something you experienced in your life, in your academic life?
I'm blanking right now.
That's okay.
Maybe you just get your energy. No.
Sorry?
Well, the derivative, temperature is an average, correct? It's just in parentheses. Well, derivative of temperature would just be.
Derivative of energy over temperature. How energy stored in the system changes if we heat it more and more.
How it's written, energy would be technically considered constant, so it would just come out and then.
No, if energy is a function of temperature and we just apply continuous derivative. So it will be an answer, how can I store energy in this system? Like in middle school, some of us may have had a little lab when you're provided with a little piece of metal, boiling water, scales, and thermometer, and you dip on the little rope your metal block into the boiling water, measure how temperature is changing, and then as a result you find the thing that I wanted to hear from Adam. Energy or temperature. How much energy can be stored in an object?
Heat capacity?
Yes, exactly. Right? Rebecca, agree? Patricia? Okay. If it is gases, then there are different like CV, CP, right? But if it is not gas, if it is just a single spin, I don't know how to speak about pressure. Just let's put it C, like heat capacity. Also, one can find an average magnetic moment of a single spin. And later on, if you have ensemble of this as function of temperature, of these magnetic moments, we can just multiply it by number of spins in the ensemble and get overall magnetization, right? So we are going to practice this approach to either one or all three of these things. And here is a story of how it is connected to real life. I was criticized in previous semesters because for giving physics examples to chemistry students, but I think there is no crime. It's not forbidden to know a little bit of physics, right? So did you try to bake a magnet? Like if you take a magnet, like maybe in a form of shape of a horseshoe, and then you put it on a stove, and then let it cool down, and then you try to pick up a nail from the bottom again. Would it be as magnetic as before or less? Okay, so same thing. So magnetization as function of temperature. So it is expected if you bake the magnet, it will become less magnetic. There are more advanced things like hysteresis. If you then put it in a strong magnetic field, it can be magnetized back. And the dependence is like external and internal magnetization makes this delicate shape with a little slit between curves. But just an idea that as temperature increases, magnetization decreases, because in ensemble, random spins are not together anymore. They're not oriented in the same direction. They take random directions, right? So there is a chance that half of the spins will be oriented upwards if you heat it up, and when amount of spins up and down in ensemble will be equal, overall magnetization will be zero, right? So we can get to this far-going conclusions just by two-level system and partition function. Okay, I'm going to erase at least this board completely and then start over to follow this story. Okay. Okay, so our first interest is E as function of temperature. And if you know that E1 is minus mu beta, E2 is plus mu, not beta, but B magnetic field. And let's assume that it is Z projection so that we do not deal with orthogonal spin. Then minus, well, I will not survive to write the letter Z. Let's assume it is there. E minus negative mu B Et plus mu B E minus plus mu B KT. E minus mu B KT plus E minus mu B KT. So you can put mu B outside of the brackets, and then we will have minus E plus mu B Et plus E plus mu B Et minus plus mu B Et minus mu B Et. I didn't lie yet, right? So in fact, well, later on we can explore derivative and redo it for magnetization, but instead of deriving more scientific equations, it's more like mathematically analyzing what we have here. Maybe try to plot it as function of temperature, and just so it's analysis of this function. There will be no actual derivations. So what do you think by glancing on this equation? I'm counting minutes toward lunch or towards the spring break. really like the fact that there is a minus on the top and on the plus in the bottom.
What do I see? I don't know. Oh,
Can you predict what would be the dependence on temperature? I cannot. Well, maybe it's possible, but I would need to like. What do you like or dislike about this equation?
Well, I mean, the dependence on temperature is as temperature increases, they become more equally filled.
Okay,
It starts mostly ground state occupied, and then after you get some threshold temperature, they're just going to be equally occupied.
would the exponentials in the top cancel each other at some temperature?
That would cancel to -1. I think.
So if temperature goes to infinity, right? Then either plus or minus, it will be e to the power 0, right? And they both will become 1. -1 plus 1 will be 0. So for infinite temperature, the energy will definitely be 0, right? So we know it. Maybe we can get more discoveries on looking on this equation. Rebecca, any thoughts?
I mean, I don't have anything insightful to say.
Okay, does it look similar to any equations that you saw before? Okay, I see Adam is nodding. Okay.
It matches with the average of the energy equals the d beta of z over z.
Yes, it is the same equation,
Oh,
right?
Yeah.
Energy as function of temperature, but mathematically, we have we add together exponentials with opposite powers. Does it remind anything?
I know if you multiply them, then they cancel each other out, and then the
Okay.
exponents become 0.
Okay, good.
That doesn't occur to adding.
Okay, but anything about adding exponentials with opposite powers?
Just gonna get e to the power 0, get 1.
Okay, let's think a little bit out of box. What if you do have e to the power I alpha, e to the power minus I alpha? Euler formula, right? Cosine alpha plus I sine alpha, cosine alpha minus I sine alpha, and if we add them together, e I alpha plus e minus I alpha will be 2 cosine alpha, and sines are cancelled. And if you subtract, then e I alpha minus e minus I alpha will be 2I sine alpha, right? So adding together exponentials of the opposite power, if they are imaginary, will give us oscillatory trigonometric functions, right? What happens if we remove imaginary unit? E alpha plus e minus alpha. E alpha minus e minus alpha. Have you ever seen it? Or do you see a symmetric connection? Maybe you do not want to say anything, but I see thought in your eyes.
Do I see a symmetric connection?
Yeah, any connection. If instead of imaginary argument, we have a
Yeah. Well, I don't know if you could say cosine, just cosine alpha.
but it looks very much like cosine from definition, right? If we define cosine as a summation of opposite exponentials, it also will be some sort of cosine. Would you buy it? Let's look in your computers. I cannot pronounce it and I cannot write it without errors, but it is a hyperbolic cosine. Cos h of alpha. So hyperbolic cosine. Hyperbolic cosine. Cosine and sine. I'm curious, what do you see? And is there a text, like Wikipedia text? Can you go a little further?
This is from Whitman, or there is also.
Okay. Okay. Yeah, just what do you see? Is there a text, like Wikipedia text for given first paragraph with definitions? So I saw each of you got the image. One looks like a parabola, and another looks like inverted tangential function, right? So there is at least one connection between sine and cosine. So regular sine and cosine look this way. And their feature is that sine of 0 equals 0, cosine of 0 equals 1. And some people just try to save, right, CH of alpha. So CH of 0 equals 1, SH of 0 equals 0, right? So at the very near the origin, they remind regular sine and cosine, and as far as we go away, they start diverging. Okay, so we can, if you want, you can tell it like mu b ch of mu b over at divided by here's sh over ch mu b over kt. If you have regular trigonometric functions, sine divided by cosine is a definition of okay. I think here should be will be hypergolic, not hypergolic. This one, tangential. Huh? Yes. I just cannot, it's hard to pronounce. I always want to say alcoholic. Okay. Mu b ub over kt. So if we would present ourselves as big theorists for theoretical community, we do not need to do any analysis of figures. We just, hey, here's the answer, enjoy. But it's not how real science is done. We need also to plot and analyze and see how this equation behaves in different regimes, right? So we do have an expression for energy as function of temperature. And we expect that the energy of infinite temperature, E for T equals infinity, will be 0, and E of T equals 0 is expected to be E1 or minus mu B. So we may want to see it as a continuous function. Ooh. Okay. I'm going to erase another panel and write there. And before doing it, I just as a little reminder to myself, I'll put here the plan. So we want E as function of T, we want C as function of T, and we want the magnetization. Enough. So let's do a table for different values of temperature. So temperature equals 0, temperature equals mu B, and temperature equals infinity. We can also put in the same table beta, the inverse temperature, which will be mu B over KT. One over KT. So 1 over 0 is infinity. 1 over infinity is 0. Let's do it KT this way. Inverse of the mu B. So let's look how the other parts of the equation of players of this equation will depend on this values of temperature. So if you get some limiting cases, we can just draw them and then connect by a continuous line and get general vision of what is going on. So E minus mu B over KT. So if KT equals 0, then it is E to the minus infinity. E to the minus infinity is 0, right? Correct me, I like making mistakes, voluntarily or involuntarily. So 0, is it right? Plug in here is 0, we get in 1 over 0 is infinity. E to the minus infinity is 0. Like here is a function of exponential e of x. If you get to minus infinity, it is 0. Okay, let's continue. Anyways, now if the temperature At equals mu b, then here we have e to the minus mu b over mu b, so e to the minus 1, which should be 1 over e. So something like 1/3, 0.3, right? And if temperature is infinity, then e to the minus 1 over infinity will be 0, e to the minus e to the 0 will be 1. Okay. And let's explore another Boltzmann exponential. So e to the power plus mu b over kt. So e to the, if t is 0, then e to the power is, e to the power infinity will be infinity. Here, if kt is equals mu b, it will be e to the power 1, e approximately 3, like 2.7, right? And if we put here if temperature is infinite, then it is e to the power 0, it will be 1 over again. Okay, I'm just looking if there is enough space, but for drawing. So let's do 2 axes. One axis will be for temperature. It will have points 0, kt, mu b, and infinity. And then we can get an axis of beta, which will have or positive. I don't know, probably it's not forbidden to call it minus beta, and then so that it goes a little more natural. Or mu beta is minus 1 over mu beta, and for infinity is 0. And then we cannot go to beta cannot swap the sign, but formally we can go to beta for going plus a positive infinity. Okay. So we do have three arguments, and we will have for our functions, we will have 4 possible values. So we can have 0, we can have 1 over E. We can have E. And we can have infinity, 1 in between. So 5 values. And somewhere at the top we have infinity. So let's look on the exponential with negative. So at temperature 0, it takes the value 0. Then it takes the value 0.3, and then it takes value 1. And somehow they're connected. So this is E minus mu B over KT. Another exponential with a positive power at 0, it takes infinity. At temperature equals mu B, it takes value 3. And at infinite temperature, it also takes value 1. E plus mu B over KT. So we do need to add and subtract these two functions to get to the numerator and denominator of the energy. So if we add them together, 0 plus infinity will be anyway infinity. We started to do cosine, hyperbolic cosine. If we add them together, then it will be halfway. It will be here and a little closer to the higher value. And when they both are equal, so hyperbolic cosine will approach 1, same as we were drawing there. If we subtract so if you literally follow, we need either subtract from negative, we need to subtract positive. So from negative, we subtract positive, we'll get minus infinity. Then from 0.3, we subtract 3. So it will be about minus 3, whatever it is. And 1 subtract 1, it will be about 0. So SH. So it is this branch that we looked from the Wikipedia, right? And now we can visually process this line. Well, those are new functions for us. We were not playing with them every day. But following these trends, we can roughly process of what they are. So numerator divides by denominator. So minus infinity divided by plus infinity will be -1. And here, it's the already energy divided by mu b, dimensionless energy. So -1. Then in the limit of infinite temperature, it will be 1 divided by 0 divided by 1, right? So 0 here divided by 1 will be 0. And since they are continuous functions, it will be something in between, in the middle. So it will be not precise, but like -1/2. So for the energy as function of temperature, if we go from 0 to infinity, we start from minus mu beta, we end at 0, and then there will be hyperbolic tangential function, right? Which will show that as closer we are to the temperature, to the infinite temperature, the energy will be close to 0 because spin up and spin down become equally probable. So we may want to right now, or as a homework, to take derivative of this function and find that there will be derivative will be 0 in the limit of temperature close to 0 and temperature close to infinity, right? And in the middle, there will be a peak in the derivative, which means that the heat capacity will have specifics. So as you try to warm up your material, it will, at certain temperature, it will accept external energy more happily, right? When external energy will contribute at most to flipping the spin. Let me check if it is easy enough to do the magnetization. So for magnetization, we can write things over, but instead we can just project the derivation that we just completed onto the situation if we need to find the magnetic moment. So magnetic moment is different from energy only by a factor that we do not have. We will not have beta here, right? No, there will be no magnetic field. There will be only magnetization. And then if we do average expectation value of magnetic moment as function of temperature from the value corresponding to spin down back to 0 because they compensate each other, and there will be a specific temperature when this transition is most probable. So it will be corresponding to the value of temperature when there will be maximum in heat capacity, right? So at the same time, heat capacity has maximum and the magnetization disappears. Make sense? So there are terminology developments for, it's called, I think, new temperature when it material loses magnetization. But this simple model deals, so single spin can be applied to realistic materials if spins do not interact, right? And the unpaired electrons in transition metals or lanthanides are excellent representations of spins, but they start interacting. If they flipping one spin will affect another one. So this is more for paramagnetic when it is a dilute magnetism, when each spin is far enough. Maybe with a dielectric is doped by magnetic ions, or it is a big molecule with very few transition metals far enough. So this approach will work for paramagnetic, and then this derivation with just two spin states agrees with the experiment. If you look on to realistic material like iron, cobalt, or in 2013, they stopped selling lanthanide magnets in the airports. Before, anytime you fly, there is a souvenirs of little spheres of lanthanides, and they magnetize very strongly to each other. I don't know why, but now the souvenirs are not more available. But if you deal with these realistic magnets, the interaction between nearby spins will dramatically modify these dependencies that we derived here in class. So the heat capacity contributed by spin degrees of freedom, and Adam will not allow me to lie because he was taking undergraduate statistical mechanics. So heat capacity is contributed by all possible degrees of freedom. Spin, electronic, rotational, vibrational. So if you focus only on spin degrees of freedom, it is what we get, right? But if, and the infinity here will be like 50 Kelvin. If you go above 50 Kelvin, other degrees of freedom will start contributing, and it will be much more rich dependence. And if my part of the course will be longer, probably I would slowly bring this stuff. But if you look on a relatively low temperature, and if we allow spins to interact with each other, this curve will become sharper, and this derivative heat capacity will become almost like a pike. So only at certain temperature, it abruptly accepts temperature and then stops accepting heat. And same for the magnetization. So it will, if we allow explicit interaction between spins, if the Hamiltonian will be so spin summation of I magnetic moment of spin I, and then if we add summation ij magnetic spin I scalar product of spin j with some coupling up front. So if one allows interaction between spins, what you did only for two spins in your other class, and process it through the methods of statistical mechanics, the dependence will become sharper, and it will be abrupt phase transition. So before critical temperature, material is magnetic no matter what. So you hit, and it stays a magnet. And as you overcome the critical temperature, it abruptly loses magnetization, and all spins become randomly oriented. Half spins will be up, half spins will be down. Make sense? So I'll check how many of your works we have for my part of grading, but I will probably share another code that will implement this thing, and you can practice it and just do your best what you can within like a couple of hours. If it works, works. If not, just write a brief report, and it will be counting like an how we can call it, exam, midterm, towards the final grade. So I think we are about finishing. What I regret in this course that because of snowfalls, I didn't include heat capacity due to vibrational degrees of freedom. There is a so-called Debye formula that agrees very well with experiment, and the mechanics of deriving this equation is very close to black body radiation. But this year it is what it is. There is no time to bring it. So if I teach this class again, I will deliver it to the next generations. And you probably will see it anyway, or you have saw it in your other classes. It's just a material that would be very appropriate here. So we started with Lebsch-Gordon. Then we did the spectral terms for lanthanides. No, we started with hydrogen and some features of the hydrogen molecule and orbitals. You were giving names for orbitals. Then we went over the addition of angular momentum and a little bit of nomenclature for atoms with large spin. The experimental complement was not very successful because of the noise from the sun. And what did we do after? I think then we did fluorescence and molecular spectroscopy through Frank-Condon factors, right? And then we did black body radiation and a little bit of magnetization. So it's, I think, sufficient material to call it a survey course, right? In the second part, some of you may, or maybe all of you will be very happy to see. I cannot say that it will be easier, but it will be material that you are more familiar. So it will be classical thermodynamics with some derivatives, entropy, enthalpy, state functions, laws of thermodynamics. So any questions are very welcome, either now or in the emails or private, just to stop by the office. I do not anticipate anyone will have problems with grades, but I will try to avoid putting 100% to everyone. I will just try to find little errors and grade it like so that there will be a little distribution, but all to the positive side, so that if you excel in the second part of the course, your grades will be perfect. If you really fail something in the second course, some of you may finally, upon average, get B. But I'll go over everything I collected and put grades. If anyone is interested, I can share. But I think it is a boring stuff. But send me an email if you're curious. I'll do it by the deadline, whatever is for putting the grades into the electronic system, which is in the middle of the break. And I'll try my best tonight to share the code for this stuff so that you can try. So I'm waiting for the fitting experiment for black body radiation, right? And then a little exercise on the magnetization for multiple spins. Yeah, I will miss you, especially Benjamin and Rebecca, because we are finishing, and for others, we'll see each other in the other class. So hope you got some fun. It was not too boring, and wishing you well for in the rest of your career, and have a pleasant spring break. I know that it's a little ridiculous of like giving you assignment and tell her pleasant break, but hopefully you'll finish it before the break starts. Okay, meeting is done. Everyone is welcome to disconnect and depart.
I remember,